We have our bowling ball. In order to convert a tough split in bowling, it's necessary to strike the pin at a glancing blow. Meaning you're letting the ball just hit the very edge of the pin, so the pin will take off at a very large angle. So assume that the bowling ball was initially traveling at 12 meters per second, and we'll assume that it has 5 times the mass of a pin. So our pin goes off with the speed of 5 meters, that's not correct, is it? 3.5, sorry. So it goes off with the speed of 3.5 meters per second at an angle of 80 degrees from the original direction of the ball. What is the velocity of the bowling ball just after the collision? We're ignoring any spin that the ball might have. So this is a collision. The bowling ball hits the pin, makes the pin move. For any collision at all, we know that momentum must be conserved. As long as we look at immediately before the collision happened versus immediately after the collision happened. So the initial momentum of our system has to equal the final momentum of our system. Our system are the objects involved in the collision. So our system consists of the bowling ball and the pin. Now momentum is a vector. So when we look at conservation of momentum, we need to look at momentum being conserved in the x direction alone, and momentum being conserved in the y direction alone. Doesn't matter what you do first. We look at the x direction. How much momentum does the ball have in the x direction initially? 0, because it's not moving horizontally. What about the pin? Also 0. Because it's not moving initially. The pin is stationary at the end of the bowling alley waiting for the ball to hit it. The whole reason the pin moves is because the ball hit it. So initially in the x direction we have a total momentum of 0. After the collision, the bowling ball has momentum. It has an x component right here. The pin has an x component as well. They're going to be in opposite directions with equal magnitudes so that they add up to be 0. So the momentum of the bowling ball, I'm going to call it negative since I know it's to the left. If you call it positive, that's fine. You'll just get a negative answer. The mass of our bowling ball is 5 times whatever the mass of the pin was, so 5m. The bowling ball will have an x component of velocity finally. We don't know what that is, but we're looking for it. The pin, its momentum is its mass times its x component of velocity. It was traveling 3 meters per second, but we need the x component. The x component is opposite the 80 degrees drawn in the picture. So we need the sine of 80 degrees to get the x component. Ends cancel. So we end up with the x component of the velocity being 0.69 meters per second. Very small. So 5 times 0.69 gives us the same thing as 1 times the 3.5 times the sine of 80. They have equal momenta in the x direction. Questions on getting the x component? We do similarly for the y component. The ball does have momentum in the y direction initially. Its mass is 5m. It's traveling at 12 meters per second in the y direction initially. The pin is not traveling in the y direction initially. The pin's not moving at all initially, so it has no momentum, period, initially. Finally, the ball transfers some of its momentum to the pin. The ball will still have some momentum in the y direction. Its mass is 5m. It will have some component of velocity in the y direction. Plus, the pin also has momentum in the y direction. Its mass is m. its component of velocity in the y direction is the 5 meters per second. We're adjacent to the 80 degrees this time, so cosine of 80 degrees. The m cancels again, so we have 60 is equal to 5y plus 3.5 cosine 80. The y component of the velocity ends up being 11.9 meters per second. So our velocity vector over here, we have a y component that's 11.9 meters per second. We have an x component that's 0.69 meters per second. Using the Pythagorean theorem, x squared plus y squared square rooted, we get 11.9 meters per second for the overall speed of the ball. So the ball is traveling at 11.9 meters per second. Doesn't slow down by much. It was traveling 12. Now it's 11.9. The angle's drawn in the picture. We just simply need to find this little theta here. Theta will be the inverse tangent of our x component, the 0.69, over our y component, the 11.9. We get 3.3 degrees. Now there's our answer. So the velocity of the ball after the collision has occurred is 11.9 meters per second at an angle of 3.3 degrees. So the ball doesn't veer too far off of its original path.